Here you see two equations involving exponents, but they're very, very different kinds of equations. And the purpose of this video is to explain the difference between an equation where you're trying to solve for some variables and an identity. So you might recognize this top equation as coming from our previous video. This is what's called an identity. And an equation that's an identity just means that all possible values that the variables might be are true for this equation. So it's just a way of saying the left side is always equal to the right side no matter what. You're more used to seeing equations where the equal sign means is us asserting that we want the left side and the right side to be equal, but they're not always equal. It depends on what numbers you plug in. And so the process of solving an equation is figuring out what values actually make the two sides equal, what values actually make the equation true. So that's the contrast. Identities are always true. Other equations are not always true. It depends on what numbers you plug in, and so you can solve to figure out what values make them true. So you know how to solve a lot of kinds of equations, but how can you confirm that something's an identity? If I give you an expression, how can you actually show that it's always true no matter what? So the way that you do it is you apply definitions that you know until you can show that the left side and the right side are actually the same. They're just different forms of the same expression. So let's try this one as an example. I'm asserted. So this is not a very helpful identity. We'll get in a second to why are identities useful. But this is not a very helpful identity. But let's try and confirm that it's always true. Here's what doesn't work. It doesn't work to just plug in numbers and say, aha, see, the two sides turn out to be the same. So for example, if x is 2 and y is 3 and k is 4, I can plug in the values and I can simplify until I get 81 over 16 equals 81 over 16. The problem here is, how do we know that these numbers weren't special, that these numbers were like just the right values to make this true, but if we chose other values, maybe it would be false. So that's why you can't show that an identity is true just by producing one example where it's true, because we're trying to assert that it's true no matter what. So instead, let's do the same simplifications you would have done when they're numbers, except let's keep everything variables. So you are allowed to modify the left-hand side or the right-hand side separately, or you can do anything that's algebraically valid until eventually you get something equals itself, because that is a way of showing that the two original sides actually were the same. So let's go ahead and apply some definitions. I know that a to the negative 1 is the same thing as 1 over a. So I'm going to apply that definition here. So this is the same as 1 over x to the k over y to the k. And if I want to take the reciprocal and multiply, that's the same thing as y to the k over x to the k. All right, so far so good. Here we've got y times x to the negative 1 to the k power. All right, let's keep this left side where it is and start simplifying the right-hand side. Again, applying the definition of negative integer exponents, we've got negative y times x to the negative 1. X to the negative 1 is just 1 over x. So now this equals y over x, and that's all to the power k. And I know that this further simplifies as y to the k over x to the k. So now I've done it. On the left-hand side and the right-hand side, whoa, got a little slanty there. So on both sides, I've got y to the k over x to the k, and so now I can see, obviously, that this is the same no matter what, because both these expressions are really just different forms of the same thing. So that's how you can demonstrate that an identity is true.